We've had series of issues, challenges with the installation of pipelines, assets in oil and gas facilities. Those challenges range from the fact that these pipes are insulated, so you don't quickly identify the corrosion aspect of it, which makes it very, very dangerous. Ordinarily, they are hidden. You don't see them. You don't see them most of the time. The outward appearance looks very wonderful. You don't know that your pipes are corroded. Okay, so it makes it very, very difficult. These pipes are looking wonderful because the coating, the insulation is looking very fantastic. Now, I want us to just watch this picture. Okay, so that before we look at the picture, the basic thing we want to talk about today is actually to give a brief explanation of what CUI is, as well as the various methods that we have presently to actually inspect CUI in our oil and gas facilities. So let's look at this wonderful picture. It says, judging a book by its cover. Now that's an insulated pipe. Now as you look at that, I'm sure you will see that nothing is happening there. The pipe is looking as clean and as fine as the very first day you installed it. But now let's see what happens next. By the time you take away the insulation after a while, you will quickly see that the pipe is already corroded. And now you can only see this when you do an inspection on that pipeline, or when you notice a leak on the pipeline, or even in a vessel. Right, so why do we have to insulate our oil and gas assets? We need to prevent contact with assets with high body temperatures. As a matter of fact, we have people working in facilities where products are going through pipes and these pipes are heated up. Okay, if they are not insulated, definitely you will find people hurting themselves from time to time. So we need to actually cover them with some sort of insulation. 2, we also need to conserve the heat energy. Okay, for purpose of conserving the heat energy, we need to insulate pipes. Now, maintain process bare pipe temperature to prevent heat stress on personnel. You find out that there are some facilities that are fully exposed. They are bare, the pipes are bare. But the heat that is being generated, if those pipes are not insulated, the heat generator will definitely impact on the personnel working in such environment. And hence, we have to insulate those pipes. It also protects the underlying equipment from adverse weather effects. Some of our pipes run through such environments where you have salt water and all that. Because you don't want those fast corrosion, you need to insulate them. Protection from fireproofing. From fire, you have to fireproof them such that, they are not impacted by fire, because that will obviously cause those pipes to quickly corrode. Now, what about noise? Because of the fluid flowing, the speed and all of that, you will realize that there will be some form of noise created. So, assuming all the pipes are carrying fluid and are not insulated, definitely you have some kind of noise, and this is actually a regulatory issue. We need to control our noise level. Now, factors responsible for CUI. Number 1, penetrations, breaches in the insulation jackets. You realize that one of the reasons why corrosion actually takes place in these pipes, these insulated pipes, is because they have been damaged to the jackets. And what happens? You have water getting into the insulation, and then going through the insulation sometimes stays within and possibly goes through if you have coating even in such pipes, okay, and then begin to corrode those pipes. So that's one of the factors responsible. The next is poor or no inspection and maintenance program. I can tell you that there are still some people, even today, that still do not have a program in place to take care of insulation, as corrosion under insulation. If you don't have one, I can tell you that your facility is in trouble. Your facility is in trouble. So we need to actually have in place an inspection and maintenance program for our insulated pipes. Non-adherence to inspection and maintenance program. Now, yes, in some cases we have programs in place, but how do we actually implement these programs? How much time do we set aside to see that, yes, these programs are well implemented? We've come to a situation, we've come to see that sometimes, yes, we have a maintenance program in place, but people don't actually obey it for certain reasons. Oh, please, we have this to deliver, so therefore, please let this inspection wait. Okay? I tell you, you're only doing more harm to your facility than good. Atmospheric conditions. Now, you look at that picture by the right side, on your right-hand side. Okay, so you see, because that was exposed, see how that pipe, which was previously insulated, properly wrapped, see the way it looks now, is heavily corroded. How does CUI occur? I did say a bit of this a while ago. Now, if you look at that very well, you see that first and foremost, there's a jacket. So if the jacket breaks, what happened? The next section of it is insulation. Now, you see water seeping in. You see vapor sometimes seeping in. And what happens is it sometimes stays between the jacket, the insulation, and the pipe itself. Within a short space of time, what you eventually see is that it begins to eat into the pipe. If you have coating sometimes too, it could get through the coating and then begin to get the pipe corroded. So ingress of water, either in liquid form, rain, or vapor. Now, water accumulation under the insulation, more technically in the space between the insulation and the coating. Now, dissolution of corrosive species, either from the insulation material or from the surrounding. Now, areas of oil and gas assets susceptible to CUI. All penetration or breaches in the insulation jacketing system includes the following. 1, assets near marine and coastal environment. Like I said sometime earlier, we have pipelines running through saltwater areas, and if they are not insulated, definitely they'll be prone to what? CUI. Assets exposed to steam vents. Some of our pipes, they are just directly opposite the vents of a steam, so definitely you need such pipes to be insulated. Areas subject to process spills, ingress of moisture and acid vapors. Certainly, if you have a broken jacket already and you have oil or whatever product dropping on this, what you are inviting is CUI. Dead legs and attachment that protrude from insulated piping. You know, you have the T-joints, you have the valves, you have the meters, the gauges, and all that. Okay, it's very difficult to actually have the insulation tight around this area. So those are areas we should focus on when we have to inspect. Vibrating piping system that have tendency to damage insulation. Certainly, there's no way you have the jackets on and you have your line undulating and you expect that insulation to still remain intact. Finally, we have those points where we normally take UT. Assuming you have you suspect CUI in a particular portion of the line. The first thing some people do is to do what? Is to go and open a section of the line and then do a UT on it. Now the question is, after you open those lines, what do you do to the insulation? Are you able to put it back the same way you met it? If the answer is no, then of course you will be inviting CUI. But we talked about how does CUI occur when there's water ingress into the insulation. It eats into the insulation and then gets across to your pipe, which you were trying to protect. So consequences of poor management of CUI in our oil and gas assets. One of them is leaks. So if you don't inspect your pipes, from time to time, you will definitely see leaks take place. And then what happens next? Pollution. The community will come after you when you pollute the environment. Fire, if you don't manage it very well. Explosion. Process interruption. Your customers are somewhere waiting for you to deliver product to them. But because you didn't deal with this very well, what happens? You're going to start losing revenue as well, because your process is going to be interrupted, and the next thing is that you're losing revenue. Then reputational loss, certainly when they hear that you are not able to manage your processes very well, of course, there will be some reputational loss. Then fatalities, some cases, yes. Because if there's a fire outbreak and it's not properly managed, of course, there's certainly going to be fatality. And then finally, regulatory penalties. Those regulatory authorities will come after you and say you didn't do what you ought to have done. I don't think that's what we want in our industry. Now, we have some records of CUI-related incidents. In 2012, for instance, in USA, there was a catastrophic explosion due to insulated pipe rupture and poor inspection decision. There was also one in 2001 in the United Kingdom. The catastrophic failures occurred in a section of an insulated pipework on the saturated gas plant at an elbow just downstream of water into gas injection point. Now, in 2003, again, in UK, there's a failure in a thermal relief line from a pressure relief valve due to corrosion under insulation. And in 2010, France, an explosion occurred due to failure of insulation in a section of atmospheric distillation. Imagine what happened to Richmond Refinery. Do you know how much they lost in terms of the facility? Okay, what about if human life was involved? So we must have it as a policy that, look, we have to deal with the issues of CUI.
The Chevron Richmond Refinery lies approximately 10 miles northeast of San Francisco in California's Contra Costa County. The 2,900-acre facility was initially established in 1902 and primarily makes transportation fuels, such as gasoline and diesel, as well as lube oils. The refinery can process up to 250,000 barrels of crude oil per day. The first step of the refining process takes place in the crude unit, where crude oil is cleaned and heated before entering the distillation tower. Inside the tower, the crude oil is boiled. The vapor then condenses into various liquid hydrocarbon fractions, or streams, including jet fuel, diesel, and gas oil. The different streams exit the distillation tower through separate pipes or side cuts that lead to other sections of the refinery. On August 6, 2012, the crude unit was operating normally. Around 3:50 that afternoon, an operator was performing a routine check when he noticed a small puddle on the ground near the distillation tower. The liquid appeared to be dripping from an 8-inch insulated pipe 14 feet overhead. The leaking pipe was a section of the tower's number 4 side cut line, which operated at a temperature of 640 degrees Fahrenheit and contained light gas oil, a combustible liquid similar to diesel fuel. Chevron inspectors knew that over the years, the walls of the number 4 side cut had thinned due to corrosion, but they did not realize how close this particular segment was to failure. There was no shutoff valve between the pipe and the distillation tower, and no way to isolate the leak. The head operator was called to the scene. Although he believed the situation was serious, he did not believe the small leak warranted immediately shutting down the unit and stopping production. Following Chevron's standard practice for responding to hazardous leaks, refinery firefighters were sent to the scene. A number of managers, engineers, and technicians gathered there informally to assess the problem. The group discussed a recommendation from an operator to shut down the unit, but they decided to first try to pinpoint the leak by removing insulation from the pipe while the crude unit was still running. They hoped they could stop the leak with a temporary metal fitting known as a clamp. A Chevron firefighter tried using a pike pole to hook and pull away the insulation, but this poking action was deemed too dangerous because it was moving the pipe. The CSB later found that the tip of the pike likely caused a small puncture in the already thinned pipe. As the unit continued to operate, workers assembled scaffolding directly beneath the leaking pipe. 2 firefighters then used a hook to remove the insulation from the pipe. As they were working, hydrocarbon vapor began to flow out from underneath the insulation. The two firefighters backed away from the growing vapor cloud. As the hot vapor mixed with air, it ignited. That fire was quickly put out, and the two firefighters immediately climbed down off the scaffolding. But the exact location of the leak was still obscured by the remaining insulation and firefighting water. So the Chevron firefighters attempted to strip the insulation off the pipe with high-pressure water. But the leak suddenly worsened, and hot hydrocarbon liquid started to spray out of the pipe. A decision was finally made to begin an emergency shutdown of the crude unit. But it was too late. Suddenly, the pipe ripped open. A vapor cloud formed and rapidly expanded as the large inventory of hydrocarbons in the distillation tower started to vent through the ruptured pipe. The vapor cloud immediately spread over hundreds of feet, engulfing all 19 people who had gathered nearby. The firefighters and operators struggled to escape through the dense hydrocarbon cloud, unable to see. They had to feel their way out, some on their hands and knees. At approximately 6:30 p.m., 2 minutes after the huge vapor cloud formed, the hydrocarbons ignited. One firefighter was trapped inside a fire engine when it was suddenly engulfed in flames. He radioed for help.
Mayday, mayday, mayday! This is Foam 60!
But when he received no response, he assumed everyone else was dead. To escape the inferno, he fled through what witnesses described as a wall of fire. Fortunately, all the workers would eventually flee to safety, and there were no fatalities. The towering white vapor cloud could be seen as far away as San Francisco on the unusually clear August day. After the ignition, a dense plume of black smoke formed and drifted away from the refinery. The fire continued burning for hours. Over the succeeding days, more than 15,000 people sought medical treatment at nearby hospitals for breathing problems and other symptoms. During its investigation, the CSB determined that the carbon steel pipe installed in 1976 had thinned to the point of failure from an effect known as sulfidation corrosion. Carbon steel piping is particularly susceptible to this type of corrosion, which occurs over time when the steel is exposed to sulfur-containing hydrocarbons at high temperatures. Steel piping that happens to be low in the element silicon corrodes especially quickly. The CSB learned that sulfidation corrosion had caused a major failure at Chevron's refinery in Salt Lake City, Utah, in 2002. Chevron then performed an enhanced inspection of the No. 4 side-cut pipe at the Richmond refinery. It revealed accelerated thinning in the piping section that would ultimately fail in 2012. Replacement was recommended, but this did not occur, and the section of piping was never inspected again. In 2009, Chevron experts recommended that every segment of high-risk carbon steel piping be inspected for corrosion. However, this was not done. During a maintenance turnaround of the crude unit in 2011, Chevron inspectors examined some, but not all, locations along the No. 4 side cut and found significant thinning. Some sections were replaced, but managers decided that the line was thick enough to stay in service and that an overall replacement could wait up to 5 more years. According to CSB investigators, a key lesson is that each and every segment of the piping should have been inspected. Most importantly, the pipe should have been replaced much earlier with an inherently safer corrosion-resistant alloy. The CSB also concluded that had the crude unit been shut down when the leak was first noticed, the massive fire likely would not have occurred. The 19 workers would never have been endangered, and the community would have been protected. For more information on the CSB Chevron investigation, please visit CSB.
2, strategy. There must be a strategy in place. Now, it's something to have a policy, but there must be a strategy in place to do what? To ensure that what we say in the policy is what we actually do. Now, inspection and maintenance program must be one of the things that we have to have in place. And that includes visual and non-intrusive inspection. We also need to ensure that implementation of inspection and maintenance program are adhered to. Like I said before, we always want to procrastinate. Say, hey, we can do this later. Let's just deliver this product, and after we'll come to this. But who told you have such time? In the first place, you don't even know what the status of that pipe is. Like the refinery assumed. They assumed that, yes, we can still make progress. Why they now open the pipe, open the insulation, they now saw that the pipe was all gone, and the next thing was fire. Okay? So we should not procrastinate. We need to thoroughly implement what we say we want to do, as it has to do with the inspection and maintenance program. Now, continuous improvement. Yes, that you use this approach today doesn't mean it's still the best approach tomorrow. That's why you see innovations, technologies coming every day on the best way to carry out your inspection in order to reduce costs and take away all the hazard and the safety issues that are therein. Now, what methods are available for us, actually, in order to deal with CUI? There are different methods, and that's why we talked about continuous improvement. Okay? There have been some methods that people have been using, and then other methods also came in. Some technologies also came in. Okay? So today, we're going to be looking at 4 methods. The first, visual inspection for CUI. This one requires you to completely remove the insulation. It requires you to completely remove the insulation. 2, okay, so now look at that picture there. You see that for them to inspect the section, it's possible that they may have seen a leak. That is what triggered this inspection. Now they took it out, and then they took the insulation out to do this inspection. That's for visual. Now 2, long-range ultrasonic testing. This requires that you need to take out a portion of the insulation for the tool to have contact with what? With the pipe for you to carry out this inspection. See the section there where they took out and then mounted the tool for it to be able to carry out the required inspection. 3 is radiography. Now this, you need to use radioactive sources. Okay? And what it can give to you is just the outside diameter reading. You're not too sure if it is even exact. Okay, that's what radiography will give to you. Now, the last is a pulse eddy current. What does this give to you? Look at that. Let's look at the comparison for this. All the methods. Visual inspection for corrosion under insulation. Complete removal. Very, very expensive. You see why it keeps changing? Very, very expensive, because you need to take out the entire insulation. And when you take it out, you need to go back and completely replace it. Long-range ultrasonic testing. This is mostly used for buried pipes. You need to remove a section of this insulation. And look at that. It does not provide accurate wall thickness estimates. Radiography. You have the health and safety issues with this. Okay? Because if you have to do this, particularly with the radium, you tell people, please stay away. And when you're telling people stay away, you are building costs for yourself, because those people are already there in the field. And they have to be paid. Okay? So you tell them, please stay away. We want to do some radiographic work around this place. And so that also is expensive, plus the fact that it equally has a health and a safety challenge. And of course, it has a limitation with the diameter of pipe that you can take. So as you begin to progress, as the diameter of the pipe begins to increase, this particular method begins to become not useful for you. And then finally, we have the pulse eddy current. What can this give to you? This can give you good accuracy, and then wall thickness measurement capabilities. It does not require contact with the test surface. So in this case, you don't need to take away the insulation. You leave the insulation on there, you just put the equipment around the pipe, and it will give you all that you need. So let's look at some of the advantages of this tool over the other one. The benefit of this speckle solution. First of all, high productivity with array technology and high resolution dynamic mode. You saw the probe with an array of probes like that being launched around the pipe diameter, okay? Now, provides a relative wall thickness measurement through lift up. Remember, we were looking at which of those methods the other time, which will not provide us an accurate wall thickness. But this provides that to you. Inspect through various types of coatings. It doesn't matter the kind of coating that you're looking at, the kind of insulations that you're looking at, okay? Just use this tool and it will provide you results. Not affected by surface preparation. You know, sometimes you say, okay, clean this up first before you get readings and all that. You don't need that. It even can function very well on undulating surfaces. Now, it detects both outside diameter and internal diameter corrosion. Unlike the radiography tool that we looked at the other time, it gives you just the outside diameter readings. In-service inspection, no need to remove your insulation. You see that if those people in that refinery had this tool, they possibly wouldn't have taken the option of going to remove the insulation while the process was still on. And that was exactly what led to that fire. That was exactly what led to that fire. So with this tool, you don't even need to go through all of that. While your process is still running, you can just go there to check the integrity of the pipes. And when it becomes necessary, you shut it down and do the proper maintenance and repair. Then, of course, it's safe. No hazard. In the case of the radiography, we saw it there, that there's a big hazard there because of the exposure to the humans. Now, sorry, there's something I want to show us here. Some other things that you can do with this tool, other than the corrosion under insulation. You can do corrosion blisters and scalps, flow accelerated corrosion, FAC, using the same tool, and then corrosion under fireproofing. Splash zone and underwater inspection. You can equally use this tool to carry out such inspection. I know some of us, we have risers in our facilities, and then you need this tool to inspect those. Then surface corrosion, corrosion under coatings, and then waterworks. Thank you for your attention. Yeah, we have a whole lot of other technologies in our booths, A22. If you have some spare time, please swing by and have a feel of what they can do for you in your facility. Thank you, thank you, thank you. Well.